All right, so we're gonna do 3 definitions, and then like I said, kind of set up how these problems will go, and then you'll practice them. Really straightforward day in here. All right, so we did our lab yesterday. All right, you all took your 3 grams of baking soda, or 3-ish grams of baking soda, and you heated it up and you decomposed it, right? And which of the equations ended up being the best equation? Second one, hopefully. All right, which was this equation? 2 moles of baking soda. You don't need to write it down. It's not relevant to the notes. Makes 1 mole of sodium carbonate, 1 mole of water, and 1 mole of carbon dioxide. So you should have measured out about 3 grams of this. Okay. And then again, it was the solid that we were measuring, and I don't remember exactly what it correlates to, but it's somewhere near like 1.88 grams is what your calculated mass was supposed to be. Did anyone get exactly spot on the number for equation 2? When you went and you measured your product at the end of the lab, was it exactly what you said it was going to be in terms of the calculation? Now, most of you were close, right? I think a lot of you were like within a few hundredths, right? But we don't typically get exactly what we calculate we should get. And that's what we're going to talk about today. Okay? This idea is we do these reactions and we do all these calculations ahead of time, but you're not always going to make exactly what you think you are going to make. Okay? So our first definition is called a theoretical yield. Okay? And a theoretical yield is the maximum amount of products produced from a given amount of reactant. And as long as you can remember a maximum amount, you're good. And this is the most. They call it a theoretical yield because in theory, it's what you should make. Okay? You measured out your 3 grams of baking soda yesterday, and it should have made about 1.9 grams of sodium carbonate. And again, everyone was you have slightly different numbers because you all measured out slightly different starting amounts, but pretty much it's 3 grams to 1.9 grams. Okay? So your theoretical yield is always going to come from stoichiometry calculations. So when we do all of our calculations we've been doing, you've pretty much been doing theoretical yields. Anytime we've been finding an amount of a product in any of those conversions we are doing, that's a theoretical yield. We just didn't call it that. That's the most we should make. Okay? We should make. And then you go into the lab. And then you physically measure out that reactant. You do the experiment, right? You measured out your baking soda. You put it in the crucible yesterday. You put the crucible up above the flame. You heated it. You cooled it. And then you took whatever was left in your crucible, and it should have looked a little bit different. Still a white solid, but a different looking white solid. And you put that on the balance, and you figured out how much product you made. Right? That is what we consider an actual, bless you, yield. An actual yield is the amount produced in the lab via an experiment. So you have to actually do the experiment. Right? Now, when we do word problems, or you take your tests, obviously you're not going to do a lab, so it'll have to give you clues in the word problem that it's an actual yield. It'll say things like, in the lab, this much was produced, or from an experiment, this much was produced. Okay? I could give you data table, and it would be how much at the end did you measure, right? So your actual yield is, I do the experiment, and I measure how much product did I actually make, all right? Now, you want them to be the same, right? You want to make as much as you think you're going to make. right? That's the whole point of doing the reaction is you're trying to make the product and you want to make the most you possibly can. You don't typically make as much as you think you're going to make. And chemists are going to calculate what we call a percent yield. And that's our way of saying like, well, how close were we to what we thought we were going to make? And this is an equation. It should be on the back of your periodic tables, but percent yield is equal to your actual yield divided by your theoretical yield times 100. And we want percent yields to be as close to 100 as we can get them. That's the goal, right? But you don't oftentimes get 100% yield. And I'll tell you that for pretty much the rest of the year as we do labs, you will find this in almost every lab we do. If we're doing a measuring kind of lab, like we're measuring how much we make in a reaction, you will be calculating your percent yield, right? Like how much did we make compared to how much we thought we were going to make, right? We want to be 100%. None of you yesterday were 100% because unless your number at the very end perfectly matched the math from equation 2, nobody was at a 100%. So the big question is why do we not get 100%, right? Like, because you would think chemistry should always work perfectly, right? Like it should happen. So we should get exactly what we think we're going to get. So turn to your table, right? And you guys are going to think about some things that maybe would cause you to not be 100%. You cannot say something like human error, all right? That's controllable. Okay, like spilling stuff just means if you spill something in the lab, you would redo the lab if you were working in an actual chemical lab. But I want you to think about, just remember what the inside of your crucible looked like. Think about the fact that we were trying to compete between 4 different reactions. Think about the baking soda we use. Talk to your team. I'm gonna give you a minute. See if you can think of something that would make you not get exactly what you think you're going to produce. Go, talk. Give you some things to think about.
Different behaviors.
Tomorrow. Today was the Today there was donuts.
You know what? Like for the FRQs when you have to go to percentages, you have to write the time maybe.
Do you have to? In
Yes.
Chem, you don't have to.
In Chem, you don't have to.
Chem has a lot less rules than other ones. I mean, you can show your work, but like, I can't even think. I can say 5% here. They don't 5% yield very often. It's not everyone, but I don't really care if you like the times 100. All right, I won't force you, but did anyone think they came with a really good idea? Oh, good things, Evan. Purity of the reactants is probably the biggest reason. So if you think about those baking soda containers, okay. First off, the lids are open and they're currently just sitting out, which is what I do pretty much every year. I leave them sitting out of the tables. They also just sit open in the cabinet back there. And pretty much every year, if I need to refill them, I just buy a new box and I just dump some in. Okay? So do you think every little speck of everything in there is all baking soda? No, for sure. There's dust particles that get in there. You all are probably not the most concerned when you're like doing reactions of keeping track of this scoop goes with this solid and this one goes with this one. So I guarantee you throughout the years, because I've had those for 4 years now, I guarantee you somebody has like transferred stuff in there. Right. So unless I bought you a brand new box every single time we did something, right, it's not going to be pure. So if you're measuring out 100 grams, but only 99% of it is pure, then you're really only measuring out 99 grams of what you think. All right. So that's already setting you up to make less than you think you're going to make because you're starting with less. even though you don't realize you're starting with less. Even if you go on the back and you looked in the storage room, you actually read the containers on some of them, it'll say 99% pure. Like, it doesn't even come 100% pure sometimes from the manufacturer, because it's hard to purify things to 100%. So that's why the biggest cause of why you would not make exactly what you think you're gonna make, right? Another thing I told you to think about is yesterday you were looking at 4 possible reactions, right? Those are all very possible for what could have occurred. Yes, equation 2 is what pretty much happens most of the time, but that doesn't mean there wouldn't be a moment where one of the other reactions could also have happened, right? So you can get, this happens a lot with organic things. You'll get what we call side reactions. And maybe there's more than one possibility for what this particular set of reactants could become. And especially with a decomposition reaction, like as the atoms rejoin as you're heating them and the water and the carbon dioxide were leaving, they could rejoin in a different ratio. So it may not be what you think you're going to make. All right. And again, that's going to mess up your calculation because you're not making exactly what you thought you were going to make. And I don't love the last reason, but I'll give it to you. It's not a bad one to think about as we like do labs for the rest of the year. But when you looked inside those crucibles, were they brand new? Right. Right. So we're banking on the cleanliness of everybody else, right? And even if you wash it with water, there's still potentially residue left behind, and that residue could also do chemistry with whatever you're adding to it, right? So it would just depend. Like, and again, you may not know that, right? And you cleaned it as best you can, but you can't guarantee. So when people do things in industry, and they're doing it for like a real like scientific study, they use either brand new glassware or they sterilize it. Like they put it in machines and they really, really, really sterilize it so that you don't have contamination as being part of the problem. Obviously in a high school lab, I'm not gonna do that. I clean the best I can, but that's always a possibility. And that would cause you to not make everything you think you're gonna make. So now we can do our math. I kind of set these up all in the same way. I'll give you an equation and then like the math will all go with that equation. So it says sulfur dioxide is produced from zinc sulfide by means of the following reaction. There's your equation. If I give you coefficients, you can assume it's balanced, and I'm not going to try and trick you and like have it partially balanced. There's either lines or there's no lines. So this one is already balanced for you. So it says if 10 grams of O2 reacts, all right, so we know how much we're putting in. It's just like yesterday, if 3 grams of baking soda reacts, if 10 grams of oxygen reacts, what is the theoretical yield in grams of SO2? So the only difference between this problem and what we have done so far is I added in the word theoretical yield. All right. All that is a clue to you that you're going to do our normal conversions like we've been doing this unit. Turn to your table. Whoever has the next birthday, I don't know who it is at your table, that person gets to pretend to be me and walk your group through the conversions. Go. Whoever's got the next birthday. Walk your friends through this conversion. Pretend you're Miss McCloud. And you obviously can help your friend too if they get stuck.
Wait, so what did you do? Oh, we know we have to double. I've got it. Are you sure you're not? Yeah, you're supposed to, because there's 2 more. How do you do that? I think so then it's 3 mold on 2 months. I know, but I don't see that. I know you don't do that.
I'm gonna put up this. If it's our O2, it's 2, it will be a yield. It's so hard, if you get, so you're so, oh, being 16, but like, it's hard. But the rest of this. You know, I can hear you right now. All right, so hopefully your person that walked you through heard me. How many times have you heard me walk you all through problems? So take your 10 grams of O2, that's your starting number. Grams of O2 on the bottom, take your grams of O2, turn them into moles, all right? Please, please, please remember that when you do the gram to mole step and we use the periodic table, please don't look at the balanced equation, all right? This is old stuff. This is what we did before we learned about the balanced equation and how it related. So when you do the periodic table, it is just 1 mole of it, and then add up everything in your formula, it's that many grams. Then we can do our new thing. This is the only real new thing in this unit is moles of one thing to moles of another by looking at your balanced equation. Every time 3 moles of O2 react, we get 2 moles of SO2. And then at the end, again, we'll use the periodic table, moles of SO2 to grams of SO2. And all you need to do is add up the S and the 2 O's, 64.06 for every 1 mole. All right, so please use your equation in the middle step, but the periodic table is always with 1 mole of it. And you should get 13.3. Starting with 3 significant figures, we'll keep 3 at the end. So this part, not any different, except for using the word theoretical yield. All right, it's the most you're going to make. So this means if I was doing this reaction in the lab and I measured out 10 grams of oxygen and I reacted it with the zinc sulfide, which you'd obviously have to have plenty of that there. If I could capture my SO2 that's being produced, I should make 13.3 grams. That's the most. All right. And then part B, it says if only 5.80 grams are produced, and this is the key phrase, in the lab. Right? Because again, when we're doing word problems, I've got to give you some indication that, okay, somebody went into the lab and did this experiment. So this tells you that this is the actual yield. And so how much did you actually make? Well, this person went into the lab and they actually made only 5.80 grams. So for your percent yield, it is always your actual yield, how much was made in the lab, divided by your theoretical, how much were you supposed to make, and then times 100. I'm pretty sure it's 43 points. Right down. Yeah, 43.6%. So not the greatest. We want as close to 100 as possible, but that's the goal. On word problems, if you ever get over 100%, you did something wrong, right? Like I'm not going to give it to you over 100% on a word problem. Now on a lab, I can't promise you what your lab data might give you. But word problem wise, I will promise you that I will not give you one that'll make it over 100%. So if you ever get that, go back and check your math. Okay? Something is backwards. It's my hint to you. So in one case, I might make you find the percent yield. We'll do that a lot in labs for the rest of the year. And then in the last part of the problem, there are some reactions where you know the percent yield. There are certain reactions that people do all of the time. And if you work in industry, which a lot of chemists do, like you do the same reactions over and over and over again. So you know what the percent yield pretty much typically is going to be. And you can use that information to figure out, okay, well, if I do this reaction and I know it's percent yield, I can figure out, okay, well, I should actually make this much when I do my lab. So you can use a percent yield and find actual yields or theoretical yields as well. So when we read this last part, same equation. It says, if the percent yield at a different temperature is known to be only 60%, okay, so we know the percent yield this time, how many grams of SO2 would actually form from 10 grams of O2. Now, it ties back to the first calculation we did. We know that our 10 grams of O2 should make 13 grams of SO2, right? We figured that out back in part A. If we start with 10 grams of O2, we should make 13 grams of SO2. But that's if the reaction works 100%. Does this one work 100%? No, what percent is it this time? 60. So we can say 60% equals our actual, which we don't know, over our theoretical times 100. And we can figure out, well, I should make 13.3 grams. But knowing that it doesn't work 100% of the time, I know I'm going to make less than that. And I'm only going to make 60% of what I think I'm going to make. And if we solve for X, we'll calculate 7.98 grams of SO2 would actually be produced. You don't have to write that on the end, but it would be an actual yield. So some reactions, you know the percent ahead of time, and you can use it to figure out, okay, well, this time with these conditions, I'll make this much in the lab. And now what are you gonna do? You have 22 minutes. Go. See what you said too. When you're writing your equations, if you want me to check them, please ask. Like before you get too far into the math. Or also don't be afraid to search online. Like the first one has nitric acid. Write the formula and then check yourself. Did I write the formula for nitric acid correctly? Talk to your friends. Go.